to this computer. Okay, so welcome everyone. So tonight the topic is going to be this paper, Coconut, Continuous Chain of Thought. Along the way in researching this, I also ran across a couple other models that we'll talk through as well. These are the papers then. So the original training large models, language models to reason in continuous latent space. We'll talk about what is that? What does that really mean? And this CODI and soft COT were two additional ones that I ran into while exploring it. So, and then there's one, the last one I thought was really interesting that is very similar in a way, but I just didn't get enough time to do that. So I wanted to put a place marker for that, but we probably won't get to that today. Okay, so this should be, I think, standard background for everybody should be familiar with. Chain of thought. We've seen this has been very popular for quite a while now, but the idea is that when you have a question that is requires some reasoning, that you would, if you prompt it to provide show your work type of thing, that makes the language model lean towards these chain of thought responses, and we typically get better results when you go through that. So this was just a simple example of that. And there's various ways that you can induce it, but here's the simple traditional part of the prompt approach. Okay. So this paper, this is the abstract for the paper, and there was a few things that caught my eye and caught my interest. Ted, have you actually been through this paper already? I know you said you had some opinions about it, but I didn't know if you'd actually how familiar with it.
I kind of skimmed through it. I didn't deep
Okay.
read this paper.
Okay. Well, please feel free to jump in if there's something that you think I'm missing or something you disagree with on that. But anyhow, this is the part that kind of caught. Oops, I can't highlight on this, can I? Caught my eye, and that is that when you're doing this prompting to get chain of thought, it's reasoning in quote unquote language space, and their perspective or thesis is that language space may not be optimal for reasoning. There may be other ways to get from point A to point B. This was kind of resonated with me when I think about reasoning and actually the whole text generation. I kind of feel like there's a thought process that occurs, and a thought is formed, and then it's laid out into words or tokens. That you don't think the words, you actually think the thought first and then the tokens. So it just kind of felt interesting to me. And this paper, they go and they have a particular approach for trying to explore this. Can we teach a model to reason without actually reasoning in language space and token space? And it's interesting that there's some problems that come out of that I hadn't really anticipated. So we'll see those when we get to it. So traditional chain of thought then, in a traditional chain of thought, you would have the prompt that we saw and the language. So this is representing the language model, token in, predict next token. You would have the question, and it would start predicting, producing these tokens that represent some sort of chain of thought. And then finally, and it'll do that one at a time, finally it'll spit out an answer at the end. So what's kind of being output here is the last state is mapped into a distribution over the token space, and then you're sampling from the token space and using that as the next input to the next cycle. So very standard stuff. In this Coconut, the way that they tweak that is that at the end of the question, you have a special token. So they introduce two new tokens, BOT, EOT, beginning of thought, end of thought. And when you're in this mode, the framework around the language model actually changes its behavior. It will now take, instead of taking the last layer of the language model and running that into a softmax, or I guess it's probably projection into the token space and then a softmax on that and sampling. Instead of doing that, you just take the hidden state of the last layer and feed that back into the model where you would normally feed the embedded tokens on input. And it does that some number of times, and then it inserts I'm not quite sure what they're depicting here by not having something here. I think this output doesn't go anywhere. It's still generated, but it doesn't go anywhere. And so that's why there's no arrow and no little brown box up there. But then they'll insert the EOT, which now says we're going to, and again, it's the framework that's inserting this EOT. It's what's around the language model that's inserting the EOT. That'll then cause this to use the hidden state, the KV cache that's been augmented with these iterations on the chain of thought tokens, these special chain of thought token, well, not tokens, but hidden state, I guess I would say, to generate the answer. So that is the tweak. That's the sum of it in terms of what it takes to make this work. We'll talk more about training and stuff like that. But is there any questions? Any questions about that? Okay.
Hey, Roger, just a quick comment.
Yeah.
So when you run it through a softmax and you pick a token, if you're doing a word problem or math kind of a thing, usually what they're doing is they're always picking the most likely token. They're not sampling anymore, right? So they're not worried about diversity. They're going for correctness. But when you do that, when you pick the next token, basically that word that you then carry over to the input in the next token position, the dimensionality of that is it's an integer from 1 to whatever your vocabulary size is.
Mm-hmm.
So let's say 100,000 at the largest. Okay. Whereas when you carry over the full latent before the softmax, before the output prediction in the softmax, then that's, say, 32,000 floats. And so even one float encompasses a lot more information than an integer from 1 to 100,000.
Yeah.
But 30,000 floats. So obviously, if the model learns to take advantage of this, there's a lot more information it can carry over to the next token position. That's presumably the thinking of the benefit of doing this.
Yeah. Yeah. I mean, as I was thinking through, Ted, there's in this mode, I don't get the video feeds, but as I was thinking it through, I realized that there is still a lot of information potentially left in the residual stream in these. Let's see, back up here in the hidden states that are now in the KV cache through here. There's still a lot of information that's left behind there that you can access, even if you have an integer as the input.
Yeah.
Yeah, but it's not.
Yeah.
It's going to be less, and certainly the early states don't have access to any of the information in the higher layers. The lower layers don't have access to the higher layers. So yeah, there's lots of kind of an information pathway there. I'm not quite sure it's as dramatic as an integer to 8,000 floats, but there's definitely a bottleneck of information there.
Right. So actually, yeah. So a lot of this information in those floats might be redundant because you could just use attention and you could just grab it from the previous token positions. Yep. So it is a lot more information, but it might not be that incrementally much more since you could just grab it. Actually, somebody in the chat was mentioning the Anthropic, on the biology of an LLM that came out just a couple weeks ago, and they have a great example in there where they ask the LLM to finish a poem that they start, and ultimately There's a lot more details, but just the bottom line is what they show is that specifically when it gets to the end of the first line and there's a new line character there, okay, because they told it write a rhyming poem and they gave it the first line, that at that point it starts thinking about what are potential rhymes with the ending of this first line. And so it clearly does not wait until it
Mm.
gets to the end of the second line to then say, "Oh my goodness, now I need a word that rhymes with it." No, no, no. It knew a long time ago
It's
that it
planning
was supposed
ahead.
to
Yeah.
rhyme.
Yeah.
Yes. But then the other thing that's very interesting about it is the the concepts called maybe I'm going to rhyme grab it, whatever, with the word rabbit. Okay. Forms at the end of the first line. And then it does not appear for the next, whatever, 8 words, 8 tokens. It is very clear that it formed there, stayed there, and that when it got towards the end of the second line, it then knew to look back to the end of the first line and find the rhymes that it was thinking about at the end of the previous line. So if it were more like an RNN, right, it would just think this and it would just propagate it the whole way, saying, "Hey, remember when you get to the end of the line, you know, rhyme with grab it. Remember, remember, remember," right? It doesn't do
Yeah.
that. It just says, "Oh, at the end of the next line, I'm going to have to rhyme with grab it. So rabbit might be a good word to rhyme." And then it does the rest of its thing. And then all of a sudden, when you get to the second to last word in the second line, it then attends back, and all of a sudden, this concept reappears at that token, and it decides, "Let me output the word rabbit here."
Yeah. I guess
So by
it
that
does.
token, what I'm saying is your point. A lot of the information just might just be living there. You don't have to like spit it out the top and have it come back in the bottom. It's already being referenced earlier.
Right. Right. Although it's depending on when it was formed, I think information can't flow down the layers in a traditional model.
Yes.
Uh, in this case, it allows it to flow down the layers, I think.
Yes,
So
that's correct.
all the layers going up can have access to that information. And that's a
Yep.
difference between um, just passing a token, like in a language model or in a language-based chain of thought. Um, that ability to flow, have the information flow back down.
Cool. Yeah.
So, and I guess it's not surprising me that it like sets it aside and doesn't deal with it, assuming that it doesn't have any, because the attention can address it, kind of like random access memory, right? Can just go address it. What would be interesting is if there was processing that it could be doing, it had enough information to be working on, could it then be working on it, while other stuff is going on, I'm working on the next token, or I'm working on this line, but I'm still thinking about the previous line. That type of thing would be interesting. So,
Yeah. I mean, if you came up with some sort of weird uh, um, um, poem structure where somehow like you had to keep track cumulatively of every line that you've ever seen. You know what I mean?
mhm.
Like I don't know, like if somehow you say like, "Oh, remember what letter that line started with," and then the next line needs to start with the letter that's five after that or whatever. But also, you can't reuse letters. So if you've used that letter that's five after again, then you skip ahead to the next one. You know what I mean? Like some kind of rule, then like you could imagine that it would just be like storing all these things as it goes, and could it be smart enough to refer to all those? I think that
Yeah,
would be an interesting concept, but there's a difference between things that it learned to do during pre-training and things that you're just trying to do with in-context learning. So the
yeah,
rhyming thing is something it learned during So it's got an attention pattern that basically knows exactly where to look at the previous end of the previous
Yeah.
line for a rhyme, right? This would be different if you manufactured your own thing. You'd have to put it in the training set. So, like, if you just trained it on this type of very weird, bizarre poem, then you could test to see if it built this really, really complicated attention pattern that managed to do something cool.
Jonathan, I'm going to come
That
right
makes sense?
back to you, but let me just finish here. I guess what I'm thinking is the language models right now does all of the effort, well, maybe not all, does most of the effort go into just generating the token? This idea that, picking what is my next sentence going to be is takes a lot more processing, it feels like, than just picking the word a or the or he or something like that. And so if it was possible for it to be somehow using those cycles, it's just going to add he was. Well, that's not a good example, but something where it's fairly obvious what the word combination is. Could you be using the cycles to do some sort of background reasoning or something like that?
Yeah.
I don't know.
Yeah. I mean, like, if you aren't using your computer, if you're idle, then, like,
Yeah,
they have the screensaver. You can donate your CPU
yeah,
cycles to
exactly.
the SETI project or the Human Genome Project or whatever, right?
Yeah,
Um, yeah, I I think that hypothetically LLMs could learn to do that, but the simple next token prediction probably isn't a strong enough reward for
yeah.
it to develop that. But
I think
yeah,
you're right. Jana,
um,
Yeah, so if I'm under, on the same topic, I have another question on the thought thing, but on this topic that Ted you were talking about, is it that it kind of keeps a pointer? It's like, okay, I need to, I need to generate some more tokens or words, and then I need to come back to this place to figure out what the rhyming word is versus generating a rhyming word and then coming back to pick it up or something. I wasn't clear the way you described it, which of these two or some other way that it was doing it. You're muted, sorry.
we probably want to spend a full session talking about this cool research from Anthropic. But super short. Uh, my impression is that this is stuff that appeared often enough that it learned how to do it in its pre-training. Okay, so this is not in context learning. This is hardwired circuits that um, the pre-training built, right? So they looked at some other examples, um, like adding two-digit numbers and some other things that it's not getting. Like here, we're talking about chain of thought, right? Where you might describe some problem that it needs to solve. This is
Mm-hmm.
this is not something, right? They're just like calculate, and they say two numbers, this plus that or whatever, right? So when we're measuring these pre-trained things, then most likely, yes, uh, the weights that it developed during training, it's probably got a pattern that it's sort of memorized that looks back at the previous new line in order to get the thoughts at the end of the previous line of the poem. Now there
Mm-hmm.
have to be other concepts active that say I'm in a poem and I'm in a rhyming poem and other
Right,
things that have to combine with it. But the
right.
fact that it's like probably just hardwired to look at the previous new line.
Mm-hmm. Yeah, cool. Yeah, we can, wait for the
Yeah.
discussion on that thing. Sounds very interesting.
I
The thought, sorry, did you have
no, go
something,
ahead.
Roger?
IRD's got his hand up, but you go ahead and finish.
Yes. So I had a question on the thought thing. You talked about like the language space, right, earlier, which I kind of get, I think. But then is there like a thought space? I mean, I know how humans kind of, there's always the thought versus language and speed of thought and so on and so forth. But I couldn't quite grok it in this context.
Yeah, I think in this particular approach, they are superimposed into the same residual stream. Um, my guess would be that it starts out as a language model. I think they use GPT-2 on this one, and Llama on one of the later papers. But it starts out as a language model. But my assumption would be as it learns these continuous chain of thoughts, that it is learning some additional thought representation that goes into the stream. It still has elements of the language embedding space because there's an example here where they start probing that as a way to see that getting ahead of ourselves a little bit, but they end up probing it and find that when you're doing continuous thought and you don't need to sample a single word, you can kind of effectively be exploring multiple paths simultaneously. And they can see that because they can see kind of the language tokens or language representations popping up in the residual stream. It's a distribution of them, but they represent, you can kind of imagine that it's following a couple chains of thought at the same time. Does that make sense?
So, I mean, like thought, yeah. So it's thought, for example, like, I could get a thought, but not a word for it. It's like, what's the word for it? Like people say that, right? What's the word for it? And then because then you assume that there's a thought, but no language or something like that. And so doesn't seem like that's what they're talking about here in terms of thought versus language, or is it?
I would say,
So can I jump in, Roger?
yeah, please.
I mean, I think ultimately we don't really know what it's going to think or how it's going to learn to think. But the bottom line is if your model dimension is, say, 30,000, okay, you have 30,000 floats on the residual stream, you have a 30,000 dimensional vector space. And if you only had orthogonal concepts, you could be thinking 30,000 things simultaneously, and you wouldn't have to constrain yourself to one word at a time. Right? So if there was some question about basketball, you could be thinking about Michael Jordan and thinking about Kobe Bryant and thinking about the Bulls and the Lakers, and you could be thinking about Chicago, and you could have a lot of sort of like intermediate thoughts that you don't have to, when you're doing regular chain of thought, you would have to literally output them one at a time in order to get them into your context, such that you can then attend back to them later on. Right?
So that's it. Yeah. So that's interesting. So if you have like, if you go with your example of like the 30K vector, right?
Yeah.
So one other argument would be that it's 30K streams of language versus thought.
Yes. Hypothetically,
right.
Yeah.
Yeah. So in that sense, it may be different than the way we think about thought versus language.
Yes, most definitely.
Okay.
Right. Nobody. Yeah. And so, but that's the premise basically, that you're going to give the LLM much more horsepower if you let it work in this 30,000 dimensional vector space instead of doing one word at a time. And then the question is, if we train it in the way that they did, which I assume, Roger, you're going to go through, then does it actually learn to take advantage of this, or is it not? Does it either A, not help, or B, it could have helped, but they just never really learned how to take advantage of it?
Got it. Yeah. But yeah, thanks for that analogy. That's helpful. Thanks.
Another way you can think of it is it can invent new words. Your vocabulary is like a bunch of points around the hypersphere in 30,000 dimensions, and there's all this unused territory on that hypersphere. And so you can put vectors anywhere you want to mean anything you want. So you have you've taken the ceiling off of the vocabulary, so we can invent new symbols for new things and new concepts. Anything it can use as a scratch memory.
Yep. Entire sentences.
Yeah, you can have symbols of entire sentences, entire concepts, and paragraphs, and so on.
Yeah. Yeah, it's interesting.
Yeah, that's cool.
Actually, I just had a thought.
Represented as a float, but may not be converted to a symbol.
Ted, can you translate that to words now?
No, I just had a thought based on what you said, Julius, that even if it didn't actually learn to do math any better, if there were just super common phrases, right? Like the United States of America, instead of it requiring 7 tokens, it could just have like this like internal, really shorthand for it. That's like a super simple thing that it could do, just to kind of compress things.
Yeah, I think there's like a couple of papers that I shared like that, like take this idea and try to build models based on that idea. You don't, so basically what we're talking about is like limitations of tokens, right? Because like tokens are discrete in space, so you cannot do much with them. So maybe it's like you need to encode like a larger chunk of whole idea into some embedding, and then you process into those embeddings. So these are like a couple of papers that I had like read about these things.
Yep. Yeah, both of those. So that was the byte latent transformer and the large concept models. Is that what those posts were? Yeah.
Yes.
Yeah, I think both of those. I'd love to go through those as well as a group. That I agree that they fit in this space of not just representing tokens, but thinking it at more abstract layer.
Yeah, which I think is kind of necessary because like language itself is kind of incomplete.
I'd like to think so too, but when we get to the results, to Ted's point, it's not clear that it's doing better just yet. Now, it may be just it's early on and we haven't explored and discovered how to make it work better. But so far, it seems like it's maybe a little more efficient, but not necessarily better.
Yeah.
Yeah, I agree. These 3 papers came out around similar times, and I kind of lumped them together, and I think they somewhat share a similar weakness in terms of how well were they able to really train the model to use whatever technique they gave it. But Roger, let's turn it back to you and let you actually cover it.
Move on. Okay. So here's just basically the 2 covers everything. I think we covered that already. Again, one of the things that piqued my interest is this idea that things every cycle through this token prediction, some are more complicated, some are easier, and they're not all the same. And thinking about them differently was intriguing to me. The author made this claim, I think somewhat unfounded, but made the claim that it would be ideal for LLMs to have freedom to reason without any language constraints and to translate their findings into language only when necessary. It happened to resonate with me, but I don't know that we have any evidence that is ideal. I think that's what we're seeking. We're still looking for that. Okay, so moving on then. So this is the approach, Ted, your comment about how do you train this. This is the approach that this paper takes. So giving a training data set with a question and multiple steps of chain of thought reasoning, resulting in an answer. They would start by, let's see, they initially just insert these 2 tokens, BOT, EOT, with no opportunity for the system to loop. So it's not, it's just getting used to those tokens in there, I think, is if I recall, is what they said. The next stage, at stage 1, what they did here is you can see they took out the step 1. Now that would be multiple tokens. That's some line, some sentence associated with this chain of thought. And they inserted instead one of these cycles where after a BOT, it's not an EOT immediately. So I know that I need to take the output, don't sample it, just send it back around and feed it into the input. They would train it at this level, and then they would continue to add more thought cycles and remove these training example steps. So it was kind of nudging it in the right way. I don't remember where I put it, but I think I have it later in here where they found that if they didn't do this, like they made the case that you should be able to, once you have this structure, you should be able to kind of train that directly. But because if you just measure it on the answer, but they found that that wasn't working. They weren't able to train it. And so they came up with this curricula that some other paper had also used. And this was the approach that they used to train. Does that make sense?
Yeah, yeah. And I think if you just, and this is probably the one of the biggest weaknesses of these types of papers, is if you just let it do thought, answer, and only train it on the answer, basically that's the reinforcement learning problem.
Right.
Right? I did 20 steps, and how do I attribute the goodness or badness of my final answer amongst those 20 intermediate steps?
Yep.
Right?
Exactly.
So the LLM has no RL algorithm, and there's no loss on the intermediate tokens in this setup. So that's why they really can't do it that way.
Yeah, it made me think that is the solution. So in here, you can't train the model against an example because we don't have examples of what the hidden state should be. But it made it so where you normally would use cross entropy loss, you can't do that now. You can't do a KL divergence or anything right now. We just don't know what it's supposed to be. But I was wondering also, Ted, the same thing is, yeah, but what if I just used RL? Now, it may take longer to converge, but what if I just used RL? Would that work? And we'll see one of the papers doesn't quite get to that space, but they get a little bit closer in the Cody, I think, paper. Okay, let's see. These are some other highlights.
A quick question, Roger. So
Yeah.
in the previous slide, thought, what is that exactly? Like, is it?
It basically means
maybe I'm missing the main point that you that you're trying to convey.
So
Sorry.
it's not a token. Thought is not a token. Once it sees BOT, until it decides to insert an EOT, and we'll talk about, they explored different ways, but right now they basically say you get 3 cycles. You get K cycles, where after a BOT, I'll give you K cycles where I'll take your output and feed that back in, loop that back in, output, feed it back in, output. And then, regardless of what this output is, I will then inject, feed the next one as an EOT token. And that EOT token says, okay, go back and look at the state that you've created in your KV cache and use it to generate the answer. Use that to guide you towards the answer. Does that make sense?
Okay, so yes, and so yeah, thank you. And so, but the way they depicted it in that other slide, they're mixing thought and language, right?
Yeah, I mean, you could.
Like in stage 1, for example, there's only one atomic thought or whatever, and then there's like all step 2, step 3 is still language.
Right. All the other ones are tokens. And again, that's what I'm saying is it's actually the framework around the model that is saying, after I see a BOT, I will be in this thought mode instead of language mode for 1 cycle. And then it's
Got it. And so
it'll
it's
say, go ahead.
Yeah, so it's almost like, in the previous diagram, it's like if I imagine changing the architecture somewhat, like, you have only one stage of thought, and then you follow it up with the regular language model, and then and then you kind of change the architecture or whatever, and then you get two things of thought, something like that.
It's not quite true. No, it's not changing the architecture.
Because if you go to the other figure, where you have both.
This one?
Not this one. Sorry.
Okay.
The one, here. So it's like, isn't it like saying you take one, if you want to just do one stage, you just take one stage of this and then of the one on the right, and then you take the rest of it on the left?
So as I understand
because it's mixing.
Can I take a stab, Roger?
Yep, go ahead.
Thanks. So as the programmer, okay, we know how the LLM on the left works. Is every time you get to the top layer, you run it through an unembedding matrix, and you do a softmax, and then you pick the token. And then whatever that token is, I copy that to the bottom as the input for the next token position, right?
Yep.
Okay, that's the way LLMs work. As the programmer, when I see a BOT token, to use your words, yeah, I'm changing the architecture. I don't do the unembedding anymore. I just take the last output from the last layer, the residual stream, and I go down and I skip the embedding layer and I directly inject that value onto the residual stream in the next position. And basically, I keep doing this until I see, C is not quite the right word, until something tells me that I should insert an EOT token instead of doing this copying thing. Okay.
Right.
And so that's what I do as the programmer who controls the LLM.
Right.
During training, what we want is the LLM to learn that I'm going to do that, and therefore to take advantage of the fact that I'm copying these brown values instead of the yellow values.
Yeah.
So we want it to learn to do something with the brown values. That's what we want.
Right. Cool. Thanks.
Is that fair, Roger? The way
I think you're right. I think that the BOT is going to be, it's a token that can be predicted by the model. So that it'll determine that. The behavior once you get a BOT is the programmer. It's not the model. And what would make the most sense to me is that somehow the language model would tell the programmer, hey, it's time to go back into text mode. They claim in one paragraph, they claim that they tried that, and they also tried just doing a fixed number of cycles. And they claim that it behaved comparable, and so they just selected a fixed number. That doesn't feel good to me, but that's what this paper did. I think it's a hard problem, probably, to know when to stop and go into language mode. But my gut is that's an important thing. That it shouldn't just be hard coded, because basically what you said is that different tokens have different difficulty and require different compute resources. But instead of there being, a variable number of text ones, there's now just a fixed number of these hidden state ones. It's just a constant. I didn't like that. That didn't feel good. But okay, so that's the training process. Yeah, go ahead, Jana.
That'll be in the next paper, Roger, where they will automatically insert BOT or EOT, and then the LLM will decide when it is thinking, and
it's the way it should be.
Not.
Yep. I think it's the way it should be. And as IRD said, IRD, what is that? What do we call you? Are you on? Anyhow, what IRD said was
sorry. It's aired.
Aired? Okay. Yeah. It's like there's the idea of forming the thought and then expressing it in text is separate, follows it. That, to me, that seems what's ideal, is you get to some point here and you say EOT, and now the thought process shuts down and you just spit out, based on some state, you spit out your thought, you articulate your thought. But we're not there yet. Okay. 7:20. All right, so here we said, okay, whoops, dang it. So we're optimizing normal negative log likelihood loss on the token prediction, but they don't use the loss on the latent. You can't have a loss because you don't know what the latent is supposed to be. So in these steps here, where you're in thought, when you're looping around, you can't have a loss there. I think I have a slide a little bit later that would talk about that. They did make note that they didn't encourage in the process, they didn't encourage it to, is this the one where they talk about, oh no, it's later on where they actually do a breadth first search. So they weren't saying compress the removed language. They just want it to say, I don't know what the difference is here. It's not trying to compress it. They're just saying set things up so that you can continue with your next step in the reasoning. This is an interesting one. So they said that you can learn through gradient descent. And I have another slide here. We'll talk about, I think, how that works. They also said, this is where they said that if they tried to train just directly, they couldn't train the models. And so they had to use this multi-stage curricula to achieve the results that they did achieve.
Wouldn't it need a loss?
It doesn't get it. So let me just, yeah, there's
some wanted to do gradient descent or something.
Okay, let me go through this because I think I can, my understanding of how the loss is going to be propagated back. So I had to do this little picture of, right, here's the attention knowledge you need, and then here's decoder only network. And in a standard model, we're going to have a sequence of tokens coming in, and all of the tokens are running through multiple layers of the transformer, projected into token space, probability, and then some sort of sampling that happens from that. So in a training mode, I can feed all of these tokens in the sequence in. I predict the next token, and I am able, using the attention masks, I'm able to reference any of the hidden state that was, or not hidden state actually, KV cache, any of the key values that were generated from previous tokens in the sequence. I can access those on the attention layer, and I will get a predicted probability for each of the tokens on the output. And then I can compare that cross entropy loss from that to the actual token that it comes next in the training data, right? Is that clear? So this is just standard transformer training. And I feed the entire sequence in, I get all the predicted next tokens, and I can feed the loss back in. So like if the loss on this token will feed back in, can feed all the way down through in that residual stream. And anytime you hit an attention that is attends to one of the key values in an earlier token, the loss gradient can feed back through that attention mechanism to another position. Does that make sense? So gradient flows down, and it also flows across. And every position contributes to that gradient. Now, when we go to in Coconut, it's a little different because I do have the same type of thing. This is on like the question. But once I got this BOT, I no longer am doing these last two bits, the projection. And furthermore, I no longer have, my training data doesn't know what the hidden state should be. And so I no longer have anything that I can generate a loss on for those positions, those thought positions. Likewise, I don't have the inputs to those positions either. Because again, that's not part of the training data. Once I get back to the EOT, I'm back into this mode where I can essentially kind of train in parallel. All of these guys are predicted, and the tokens, you're going to have a loss associated with each of these token positions. So to your question about like how does the gradient flow, I initially thought they meant like since I'm stacking these, it's kind of just a tall stack of transformers, and I just have the gradient flow all the way through that. But I think what actually happens, because I don't think this is not actually connected to here. This token is just directly injected. I think what happens is the gradient flows down like we saw it before. And when I have an attention to anything in this layer, in these thoughts, I have a gradient that flows into those and will flow into the weights in these thought cycles. And of course, it can also attend to earlier, so the gradient can skip over this and flow to the earlier stuff as normal. But I think actually the gradient isn't like down through the stack like this. I think the gradient actually is going to be across. No, wait.
So that's accurate. That's how the gradients That's how the gradient starts. So if you look at your rightmost internal thought, and if you look at the top, the last layer, okay, because there's no token prediction, there's no gradient coming from above.
Yeah.
But as soon as you get any attention on that, then in addition to the attention gradients that come in from the right, now you have a gradient signal on the last layer of the last thought, and that can squiggle through all the layers of all the previous thoughts.
Yeah, I see that. As I was describing it, I realized that. Yeah. So it gets in through attention. It could get in at any of these columns, but once it's in it, it can flow through the zigzag.
Yeah. Now it might be a much smaller gradient for all we know because it's such a long path.
Yeah.
Right? Might be a vanishing gradient problem, but nevertheless, there is a path.
Yeah. So that means
Makes sense.
What I was
Sorry.
noticing, whoops.
Sorry, like question.
Go ahead.
So that would like make it like more reasonable to have like a dynamic BOT and UT tokens, because otherwise like the model might learn like, oh, like I'm just gonna generate like first 2 tokens as garbage, and after that like I'll like actually generate the stuff, right? Or like am I missing something? So let's say like if you fix like by chain of thought steps as like 2 or 3, so the model will always like generate some random stuff and go like, oh yeah, first 2 things are gonna be random all the time, and then after that like I start to generate stuff.
No, I mean, during the training process, those steps should be guiding the following steps that are going to generate text. It should be guiding them towards the correct answer or to the next step. So I think the gradient flows back and will cause this to, guide the residual stream towards the right value.
I see.
Yeah.
Not sure like I quite understand how it works, but like I'll like look into detail later.
Okay. What I'm not quite sure of is, so let me go to the problem. So that the problem that I had thought of before was you don't have any tokens, you don't have anything here to insert into these. Well, they don't need it because it's looping around, but you don't have any outputs to generate a loss from. And that was one issue. Ted clarified me in terms of the gradient flow. When you're generating, so when you're in inference mode, when you get to where you're generating, so this is to model, I should have maybe done a little bit before, but the idea is there are a whole bunch of KV cache that's been filled by that you can do all at once from the question. And when you're in this mode, these guys will be able to reference that. But you would be doing it normally when you're doing inference, you're doing 1 token at a time anyhow. So each time you go through, you'll generate the token based on what you had before. So during inference, it's not really that much different because you go a cycle for every column anyhow. But during training, normally this all happens at once. Like all of these layers get executed at once and you get the predictions for all token positions. But when we get to this place for the continuous thinking, you can't do that because you don't have the tokens to feed into here. You have to run once through this cycle before you can run the next one, run the next one, run the next one. So it gets into this sequential mode. So one of the strengths of the transformers, as I understood it, is that you can take a long sequence and you can basically run them all up using the attention mass. You can run them all up and get the loss, generate the loss very quickly. In this mode, once we throw in this kind of almost a stack of transformer blocks, I don't know how they do it exactly, but before you can do any of this stuff over here, you've got to go through the sequence for this continuous chain of thought. That's a problem I hadn't thought about.
It's basically an LSTM with attention, right?
Yeah. So you think of it as an RNN, and you have to backpropagate through time. Now, it's been too long since I read this paper. I don't know if they valued that squiggle path. They could have just said, we're going to approximate the gradient by putting stop gradients everywhere and train them all in parallel and only use that attention gradient that you were talking about initially, Roger.
That would be for the gradient pass. You still have to have it for the forward pass, though, right?
Oh, yeah. For the forward pass, yeah, you do it 1 token at a time.
Yeah, that's
But
what I
for
was trying to
learning,
think.
they could, yeah.
I had thought in my head, I had thought that it just gets propagated through attention. It didn't occur to me that, oh wait, once it gets into this column, it can propagate back down to the top layer of the next one. So I'm not sure.
There's some paper that I read, and I can't remember if it's this one recently, where they had something that was RNN-like, and they were just saying, well, officially that's how we should do it, but I don't think that gradient's that important, and it's going to be a lot easier and faster to train. And so they zeroed out all the gradients at the bottom so that they wouldn't have to do the back propagation.
So they do the forward pass, but they just stop gradient on the backward pass.
Yeah, and I mean, initially you're doing training, right?
Yeah.
And so then they trained it every token position in parallel, just like normal, to make their life easier, even though it's not quite proper.
Yeah, it feels not quite proper to me.
Because I mean, theoretically, yeah.
Although
whatever.
I guess if you're Ted, if you're doing this through curricula training, it may be that you train this initially through cross attention, and then when you move to stage 2 and you have the second one, maybe you're mostly training the second one. This one isn't really getting updated quite the same way.
But they also share weights. So there's not really a second one and a first one. But you're right. When you have only one thought token, then it is legit to train it in parallel because there's only one of them. There is no thing, right?
Yeah.
And so yes, I think that's partly why the curriculum thing helps train it a lot faster.
Yeah. Anyhow, so unless they do the stop gradient, this introduces a problem both in the forward pass and in the backwards pass. And if I'm thinking about running batches, and I don't know how big their batch size was, but if I'm running batches, I also got to think about any time this BOT might occur at different places. So I go into this different mode and iterate instead of doing it in parallel multiple times or something. So this introduces complexities, I'm sure. You could probably work around it by using attention masks and whatnot, but it's complexity. And it's going to be performance. Okay.
So I just peeked at the paper, and it looks like they say this business of the multiple thoughts and that squiggly path you drew. Really like the diagram, by the way. That makes it very clear. They said that this is a problem for parallelism, and if this technique ends up being great in the future, someone's going to have to figure out the performance issues.
Yeah,
because this isn't parallelizable.
That's the detail.
So it looks like they did actually do the full gradient through that.
Okay. Let's see what else. So we're going to look through the results. They used 3 techniques, the GSM-8K, which we've seen before. I hadn't heard of Pronto before, but Pronto is basically, I think it was a couple step reasoning. And then they felt like that from their results, it wasn't hard enough. And so then they created a new data set, PROS QA, which we'll look at real quick, to try to stress it more, and then you could see it differentiated. The net result is, using continuous understanding to be beneficial reasoning, mirroring the effects of language reasoning chains. Mirroring the effects of language reasoning chains. So not exceeding, but close to that of language reasoning. And then on these more difficult ones, and in particular, the one they created, then it can surpass the language-based chain of thought. So these are the data sets that they looked at. I didn't do a GSM-8K, we've seen that before, but in here, this was the Pronto QA. So here's an example, a set of, I don't know what you would call these facts and relationships. And you have to reason through to get the correct answer. I don't know if you'd call that linear or not linear. I think the one that they created is similar in the sense that it has all these nodes and edges that they define, and they just make up. They're trying to make up random stuff, maybe so it doesn't interfere with the pre-training. Like if you say, I don't know, a human is related to a monkey, an ape. That's something it already knows. So if you tried to ask a question that was contrary to that, it can be biased. So they just make up these artificial ones. This is the graph that they look at. When we were talking about kind of graph data sets before, this is the one that they have created for this. And it's got distractors and more complicated relationships. In the end, it's about following the edges to the right answer. But yeah, it's supposedly more complicated than the ones they'd seen before. Any questions on those two data sets? Okay. And here's the results. So as I see it, there are some of these I didn't fully understand, but so this is a language-based chain of thought against GSM-8K, the Pronto, and the new one that they've created. And this is the results. Again, I think this was GPT-2. I don't know what model size. But if no chain of thought, they would get accuracy substantially lower. So chain of thought really helped. My assumption is this is like prompt-based chain of thought. ICOT, I had to look this one up. ICOT is another basically training regime that they go through to try to get implicit chain of thought. So they initially train it on chain of thought, but then they kind of just remove one step at a time, the first step, then the second step, then the third step type thing. And it gets to where it kind of has similar results, but without going through all the language tokens. So the implicit chain of thought did a lot better than no chain of thought, but not quite as good as the language chain of thought. Pause tokens, I believe, again, I didn't look this one up, but I believe it's just, you just throw in a token and the language model can use that cycle, that compute cycle to do something. It doesn't have to worry about generating the next token. It can do some reasoning in there and then make the prediction afterwards. But it doesn't look like that on GSM-8K. It didn't really help much over no chain of thought. And then Coconut, that's theirs, and they did a couple ablation studies. But the bottom line of the Coconut is much better than no chain of thought. But it isn't on GSM-8K as good as the language-based chain of thought. If you flip over to the Pronto QA, chain of thought is already pretty good, language-based chain of thought. These other ones, wow, even no chain of thought was reasonably close. The implicit chain of thought did just fine. And the Coconut did, I'm going to say in the equivalent. They both did really good. So that's why these guys came up with, okay, well, let's make something that requires more reasoning. And now the chain of thought is not doing, has dropped. Its accuracy has dropped. Interesting, I hadn't noticed it's almost down to where no chain of thought accuracy. The implicit did pretty good, but the Coconut did even better. Well, actually not better than this, but it did a lot better than the language-based chain of thought. And then the thing to look at is that, like in this case, it doesn't do as well accuracy for the GSM-8K, but if you look at the number of tokens it took, so that would be the number of cycles, it gets it done in 3 times fewer tokens. And over here, it's, yeah, even more. No, that's exactly 3 times. We're very close to 3 times more, fewer tokens. So it's going to be going faster. So here's where kind of my gut feeling was, okay, what I see is not more accurate thinking, reasoning process, but just a little bit more efficient thinking process, or reasoning process. Ted, did you have any comments there?
No, the ablations are kind of interesting. I, yeah, I don't
I
know how much you
particularly didn't
plan to
know.
talk about this.
I didn't uh, know what pause as thought as an ablation versus pause token. I wasn't quite sure what pause as thought meant.
Yeah, it's your yellow highlighted stuff below the
Yeah.
results. So basically, without thought, it looks like they train it normally, but then the BOT EOT thing, they just don't give it any. And and that really helped on the Pronto and the Pros, even though it doesn't get to use those thoughts. It
Yeah.
just
What's the difference though between this one and this one?
the pause token was trained with regular language modeling, but an extra blank token position. That's the
Okay.
pause. This one was trained coconut style, but instead of copying the latent from the bottom, it just got a free token. So the copying made a difference for GSM-8K. So
Mm.
just giving it extra blank tokens did not help it that much for GSM-8K, but copying it down did help.
Hmm.
So I feel like the pros, at least the example you showed, right, is Alex a bumpus or a grumpus or whatever. It's kind of doing a bunch of binary logic, and you can
Mm.
see how that could be compressed into fairly few tokens, right?
Right.
Like
Yeah.
that graph, if you had sort of what we were talking about, a direction for each of the different concepts in those yellow boxes, you could sort of represent them all and hold them all in one spot, right?
Yeah.
But in GSM-8K, if you're saying, started with 8 apples, tripled the number of apples, bought 10 more, gave away 25, how many they have left, you can't really represent those with just like binary directions. You really kind of need to have numbers and do math.
Yeah.
And and that's where I think the compression hurts you, especially if you were not pre-trained in a way to incentivize like representing complex numbers in a very compact way,
Yeah.
right? 25 could be represented as a floating point number, but it's not. It's a 2 and a 5 and it's, whatever.
Yeah. Yeah. So it's kind of disappointing that whatever this technique is doesn't apply to this test case, this benchmark that we know. It really excels at a benchmark that they invented. And to your point, it might be kind of this architecture or this training method is specifically benefits from this particular metric. Anyhow,
Yeah.
any other questions? I'm gonna speed up a little because we only got 15 minutes left.
Yeah, go for it.
One of the questions I had is how many they had this graph of as you add more thoughts per step, then you get an improved accuracy. But I didn't see exactly what the number was they used for this GSM-8K. They only gave those two examples. For one of the other one, Pros QA, they showed an example of adding more. 3, I guess, was the example. But that might also correlate with like the number of the number of edges that you have to track down. I was a little unclear about that. So anyhow, yeah, they said that it helps in certain data sets, pros, QA, but it doesn't help it on like the GSM-8K. We already looked at this, ICOT. They did mention that there's evidence that it does kind of this breadth first search. This is where they were doing probing, looking for, I guess this is on the graphing. So they're looking for it, thinking about the correct node, and it's exploring multiple simultaneously. That's what the first thought is, and then second thought you've kind of narrowed in more. And they do that by this interpretability where they take like the output, they assume they put the LM head back on top of it, and they output the distribution, and they're looking for the answers that you might need at that step along the way. Did somebody speak up there?
Yeah, I was going to say, for what it's worth, breadth first search makes sense for what we were talking about. Is instead of having one token, I'm now giving you a vector space. And so if you say, you know, Alex is a Wimpus and Alex is also a Bimpus, then like you can just sort of say, oh, let me just like have a one under Wimpus and a one under Bimpus, and
Yep.
And then if it says every Wimpus is also a something, right? Then you can like see how you could just like sort of keep a bunch of true false, keep all the
Yeah.
trues in each step, and grow your uh 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 your closure of provable things. You could just grow one step at a time each time, as it
Yeah.
were.
I think that's what it was. So like they were probing and finding these four nodes at the output of the first one, right? So okay, I'm exploring. I'm an Alex, so I could be one of these four things, right?
Yeah.
And then they would explore the next layer, and they could probe and see those in. That's the way I understood it.
Right.
Even though
And
it's a
so
plot, there's still some language in it.
exactly. So for a graph with diameter 6, then you need a minimum of 6 steps in order for the breadth first search to always reach everything and then hit the transitive closure.
Yep. Yeah, and so this is kind of saying the same thing, thinking of it as a value function for each node, given the constraints that you have. Okay, so these are my thoughts, just opinions. I like the idea of the abstract, the kind of this idea that thought and language are two different things, and trying to separate them and let it think in a non-verbal way. I'd like that. I didn't kind of anticipate what that meant in terms of that the trainability, where we can no longer do a parallel train, that we got certain nodes that we don't have loss for, and we have to cycle through multiple times to get through those thinking stages, cycles. I didn't like that they didn't, during inference, they don't address the end of thought. The whole premise is that, hard problems need more time to resolve. And to me, it just seems like that means that oh, I'm done thinking should be part of the process. And it may be that they agree with that. It's just that the first step they didn't get to do that. And then the results, I would have hoped that it was a little bit better results. It was kind of disappointing to see it was lower performance, especially on the GSM-8K, which seems like a good reference. But some reasoning tasks, it's better, but that was also, of the ones we saw, that was the one that they created. So a little disappointed there. So, Ted, I know you had kind of felt a little disappointed in the paper as well. Is that any other thoughts to capture?
Yeah, I mean, I think one of the big things with this and the other couple papers that Erd mentioned, right? The byte latent and the large concept, is you don't see the idea that you mentioned of the LLM telling us when it's ready to be done with thinking.
Mm-hmm.
That seems to me to be something that, if you think about like DeepSeek R0, is there a way we can kind of combine some kind of reinforcement learning training with the idea of how long am I going to think? So I think that's one of the biggest ones for me. And I also think the curriculum makes sense as a way to try to get it trained quickly, but it seems, I'd have to go back over the details, but it seems sort of improbable that if they took a pre-trained model that's been trained on, like 2 trillion tokens of language, and you do, however many thousands of training cycles where you just replace strings that are step 1, step 2, step 3, that you pull those out, and like how deep is it really going to be, right? Like we talked about what it might represent with this 30,000 dimensional vector space. I don't think it's going to be able to learn anything too complicated uh, in that small amount of training.
Yeah, well, and it's kind of just learning the steps that you provided, right? Which, to your point, like if you did this in an RL fashion, if you could figure out how to do it in an RL fashion, it's going to learn the optimal way to get there. And you're going to want a curricula. It seems like the curricula should be not how many steps do you learn, you internalize, but rather how complicated is the problem. You know, you gradually make it more and more difficult problems.
Mm-hmm. Yeah, yeah. So I had this thought that if you did something akin to you in your regular pre-training, you've got 2 trillion tokens, right? And probabilistically, you just say at certain points, I'm going to randomly insert this BOT thought EOT sequence.
Mm-hmm.
Okay. And so you're like, what are some good places? Well, maybe I'll insert it with certain probability every time I see the word equals. You know, something equals, put some thought in there, right? And da 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 da. And then uh, in that way, let the model learn what to do with this continuous thought space or one of these other methods in a much more fundamental way.
Yeah.
As opposed to just fine-tuning something that's at this point pretty hardwired, you know. We know that the weights of the LLM are sparse, but the expectation is that the residual stream is pretty well packed at this point. So,
yeah.
That's actually kind of interesting. I didn't, sorry about the noise, like it might be a bit loud in the background. That's kind of interesting to think about it. I completely thought in the different direction. So I was thinking maybe you could have like a reasoner as a separate model that like just reasons and gives you some latent embedding space. Okay, like that embedding has like all the reasons about the prompt, right? Like it has like completely thought about that, and then you just concatenate that into the original model's embedding. And that's the direction I was thinking, because like even like if you think about how humans do, right? You ask them a question, they they come up with an answer in their head, and then they start generating the text. So that's the line of thought like that was I was thinking.
yeah,
Your
that's a
comment, like
cool idea. The problem, though, is you still need to figure out how to train your reasoner. You can't just train it on 10,000 fine-tuning steps because it needs to understand everything about the basic language, and it also needs to know how to reason. Right?
If I understood, so this was one that we've talked over in the VSLM subgroup before, but I think that the idea is that you have something that thinks in a concept space, and it ejects it emits a concept, and then something that takes that concept and thinks in a word space, a language space, and generates the text associated with that concept. Is that kind of where you were thinking? Uh-oh.
Oh, he put something in the chat. Yeah. Sorry.
Oh, okay. So we lost him, but
yeah, emergency. He had to
okay.
run.
So I'm gonna do. We got 5 minutes. I'm gonna run over by 5 minutes. I'll try to get these next 2 done in the next 10 minutes. So this Cody was the other one that came up. They hypothesized that it was actually this training process. They make note that it still falls behind the GSM-8K, and they believed it was this curriculum learning strategy itself. And so they came up with a different approach. And this is the picture of their approach versus Coconut. So in language training, it is supervised fine training. This would be the kind of traditional. You'd be training it on language. So you've got a loss function that you can generate for all these tokens. Coconut, we started out with those. You got your reasoning steps, and you move them one at a time until you've got all the steps working as continuous thought. That was their approach, stage 1 through N. And in Cody, what they did instead was they took the language as kind of the standard, the golden standard, or the teacher, I guess is the accurate way to say it. And then they use distillation to directly train the continuous chain of thought model based on matching the teacher. And they do that by matching the hidden state of the last token at all layers. And they run a KL divergence between those two. So you're trying to get this guy to generate the same hidden state in that token position as though the same hidden state as the teacher would have generated. So it's kind of, this is providing the signal. It still doesn't say what all the ones in between are, but it's saying this is the hidden state that you want to get to. So it is kind of training on a hidden state now. Instead, you got something to train on. It's just through a deeper model here. Does that make sense?
So then they really were saying that the answer has to teach all of the thought tokens that came before it.
Yeah.
Okay.
Yeah. So you can imagine if this was fewer steps, that gets easier and easier, right? I mean, imagine one step and you've got it's a KL divergence. You've got your training signal. They're using
right, except but they didn't do a curriculum, so they really did have to do multi-step backprop all at once.
Yeah, yeah. They didn't do a curricula. Here's where you could think of a curricula not as in the way that Coconut did, where they removed one step at a time, but you could do a curricula in that you could do it easier problems to harder problems. I can imagine something like that. Okay, here they got a little better results. So in the GPT-2, they actually, not exactly matching, don't know what the error bars on this, but pretty close, right? 44, 43.7. That's in GSMA-K. I didn't really look at the set of distribution stuff, so I can't speak to that. I didn't quite understand why this would be different. So they found that this is, they didn't say what model size they use for GPT-2. So I don't know.
No, it's small. So it's pretty tiny.
Oh, this one does say small. Okay. Yeah. Yeah, that's really small, right? Isn't that's a few hundred?
12 layers, if I remember right.
Yeah, okay. I'm not quite sure how I could explain this, why it falls a little bit behind when you get up to the 1 billion. But it's
still a lot fewer tokens.
Yeah. Well, they're not saying how many. A lot fewer tokens, you mean that have to be generated?
I mean, if it's one thought token replacing an entire sentence, that's a lot fewer tokens.
I don't think they said one replacing the whole sentence. They still have, over here in the student, they still have the zigzag for K steps. And they might have said somewhere later how many Ks this is. How many steps these were for, I didn't make note of it. But anyhow, so using this different training strategy, they're getting a lot closer, and this maybe needs some exploration, but at least in this space, they did as good. So that's kind of cool. And it's done presumably with fewer, I'm going to assume that it's kind of the same range of that many fewer tokens than if I was solving it in language space. So, 3 times faster reasoning. Okay, so that's the Cody. And then the other one, it was called soft chain of thought. In here, their Coconut did it this way. So you can make note of the colors of the boxes and the lines. So in a standard traditional chain of thought, you've got the instructions and then the reasoning question, and it starts doing, generate a distribution sample, generate another distribution sample, et cetera, until you get to an answer. And the little fire here means that we're training the whole language model for that. And Coconut, instead, we're getting the instructions, the question, and I guess that's maybe the BOT token. But now when you generate this solid line You can see solid line is computation in continuous space. So you're passing the entire hidden state through, and then you get back into this reasoning that it's actually not, depending on which stage, you may have some reasoning left over where you're doing sampling to generate the token. In this one, what they're doing is just inserting a couple tokens into the sequence. Well, soft thought, so it's not tokens, it's actually going to be into the embedding. And then they use that to kind of guide the rest of the reasoning. And the place that those come from is the assistant language model. These are both frozen. They're just, the only thing they're training is the projection module. I got this sense that this was maybe on a smaller budget. And so they're trying to get by with, less training. But this one, using this approach, actually was getting to where they were doing better than the zero shot in the GSM-8K. And this was interesting. Quinn actually, that's interesting how the zero shot Quinn 2.5 is better than the Llama 8B. Oh, 2.57B is better than the 8B. So anyhow, so that kind of the award that they get is that they're exceeding on GSM-8K now, and presumably with three-ish fewer tokens, they're getting a higher score. Okay. Any questions on that? So still kind of continuous thought space, just a different approach. There's one I didn't get to, which is a recurrent depth approach to test time compute with latent reasoning. This is where essentially they're looping. It's kind of the same thing, but they're looping internal to it rather than going around to the next layer. So structurally, I think it's going to be pretty similar. You're just looking at it, kind of looking at the zigzag. Instead of a zigzag, it's a conditional length. And I think they talked about having some sort of
this recurrent paper, Roger, has an additional wrinkle that's pretty significant.
Okay.
Which is that what they do is they say, oh, maybe you have a medium-sized llama and it has 36 layers. Okay.
Uh-huh.
Instead, what they replace it with is a llama that has 2 layers at the beginning, let's say, 2 layers at the end, and then they just run this one special middle layer 30 times through itself. So what they're saying then is essentially the 30 intermediate layers are virtual copies of each other, sort of.
It's just one layer in the middle?
It's one set of weights
that
runs over and over again. So the size in terms of GPU memory of this model is way, 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 way smaller than a regular LLM.
Yeah.
Because the R just gets repeated a gazillion times.
Yeah.
Zillion is an exaggeration.
So you kind of, instead of, we share weight across the sequence already, this is now sharing weights in the stack. Very cool.
So if you think about a regular RNN, right, in time, it's sharing the same weights.
Yep.
And so that's what is happening. So that's a very different wrinkle from, I thought it might have been more of a thought recurrence thing, but it's really not. It's really a layer recurrence thing.
Yeah. Cool.
So this really doesn't have anything in the token dimension that it's doing thoughts. It's just doing it in the layer dimension.
So it kind of leads to the idea that you could get by with much smaller models if you have more test time compute. Much smaller models. My phone is a lot smaller model, but it takes longer to answer the question, but it can answer just as good as the big model.
Yeah, and then they had, if I remember right, the exact same thing where it's like, oh, the model should tell you when it's done recurring. But no, they hard-coded it.
Oh, all right.
We'll do 6, we'll do 12, we'll do 20, whatever. But they just hard-coded it at a number. There's some interesting things if we want to talk about that paper, but it is
I'd like to do it. I mean, I'd like
I
to
saw the
hear about
title
it.
and I thought, oh, this is very similar, but it actually ended up being very different.
Yeah. And IRD's off, but yeah, I agree with him on those papers. So,
Yeah.
all right, that's it.
Very cool. So, that soft COT, I had a thought, well, maybe I should let you formally end things and then I can share.
No, that's kind of the end. That was my thoughts already captured. So,
All right. So maybe we'll end the recording here.
yeah.
Kind of what I was getting at.